After presenting the transfer function and the characteristic equation with the modeling, we'll go to the state space. In fact, the main advantage of using a state space is that you are able uh, to measure the output at intermediate points of the system. Why we have using this? Because of some limitations in the tensor function system. Uh, these limitations can be resumed by the following: that it does not know what happens within the system, as we have only the relation between the input and the output. And it cannot help in troubleshooting. And with troubleshooting, we have uh, to measure the outputs at intermediate points of the system. So the characteristics of this modeling is that it's mainly used in time domain. We get the intermediate values, and we are able to go from the state space model to transfer function model. So first, let's define the main parts or the main components of a state space model. First, the system variable, which is any variable that responds to any input or initial condition in a system. The state variables, which are the smallest set of linearly independent systems variables, such that the values of the members of the set of time t0 along with known forcing functions completely determine the value of all system variables for any time t bigger than t0, and the state variable vector, which represents the state variables. So the general form of a state space model is the following: x prime equals ax plus bu, y equals cx plus du, whereas x is the state variable and x prime is the derivative of this state variable, y is the output and u is the input. As for the matrices, A is the system matrix, B is the input, C is the output, and D is the feed-forward matrix. As for the procedure, it's as follows. First, we have to determine the characteristic equation of the system. Then we have to determine the number of state variables based on the characteristic equation. And third, we have to compute the four different matrices. In fact, if a system is of order n, we will have n state variables. So if a system has in the denom S4 is the highest order, S4 will have four state variables and so on. And we have two different cases regarding the inputs. If we have only the value of u of t with a constant, of course, we will use one presentation which is a specific one. Whereas if we have u of t along with its derivatives, for example, 3 of t plus 5 u prime of t plus 6 u double dot of t, we will have another generalized form. This form will not be considered along this course. As an example, let's go back to the modeling of this system, the RLC system. We have the input U, which is V1, the output Y, which is V2. This system has been modeled before as being a second order system. It is 1 over LCS squared plus RCS plus R. So as we have a second order system, we have two different state variables, x1 and x2. x1 will be equal to the output v2, whereas x2 will be the derivative of the output, so it is dv2 over dt. From this we will be, so x1 prime will be equal to x2, and x2 prime will be equal to the minus 1 over LC x1 minus r over L x2 plus 1 over LC, whereas the output will be equal to x1. To do it alone. So as we have a third order system, we will have to have three different state variables, x1, x2, and x3. x1 will be equal to y of t, x2 will be equal to y prime of t, and x3 will be equal to y double prime of t. We then calculate the x1 prime, x2 prime, and x3 prime. as I have started in my presentation concerning this part, we are able to go from a state space model to a transfer function model using this formula. So y of s over u of s equals c si minus a minus 1 b plus d. So what is the si? The I is the identity matrix. It's where the diagonal is equal to 1, the other values are equal to 0, and s is the Laplace transform, Laplace uh, variable s. And so using this approach, we can go, we can find the TF, and here is an example. So Si minus a, S I, it's the diagonal will be equal to S, all other values will be equal to 0, and here is the A matrix. So SAI minus A equal to this one. When doing the minus 1, we'll have this value multiplied by B and C plus D, we'll get this transfer function. So to summarize the whole thing, we'll have the characteristic equation, which is the following. We can go through the SS model, the state space model, the transfer function model, and the uh, block representation, which will be represented later on. And here are the complete links between these four models. So the last part of this presentation will be concentrated on the block reduction. For the block reduction, we'll start first by presenting the different relations or simplification techniques in order to get a simplified block. I just want to remind you that if we start by a very complex block, at the end of the reduction, get, we must get to the point where if we have one input, one output, and between them we'll have only one block. So the first reduction will be at the level of the summators. So here is that summator. If we have several summators, more than two inputs, in fact, we have to divide them into several summators, each one having two inputs and one output. So for example, we divide this into two summators, R1 and R2 with a plus sign. The output will be connected to R3 with a negative sign, so we'll have at the end R1 plus R2 minus R3. So here if we have the G of S block after the summator output, we can insert it along with the input, which with each input R of S and X of S before the summation, and at the end we will get the same output, which is C of S equal R of S plus X of S the whole times G of S. In fact, here, if you want to put the G of S at the end, we have to divide the input X of S by 1 over G of S in order to output. If we have several summators, how to add them, which is the parallel form. If we have several summators in cascade, which is a serial form, we have to multiply them one by the other. Also here, if we have a block at one output level, we can multiply it as being the input and divide the values of the value of the block by the other inputs. Here is a case for the feedback system. So first G1, G2 and G3 must be multiplied together. They are in series. The same goes for H1 and H2. So G of S will be equal to J2, J3, and G3. H of S will be equal to H1 times H2. And as we have a feedback system, we'll have the transfer function between R and C equal to G of S, which is the feed forward over 1 plus G times H if we have a negative feedback, whereas if we have a positive feedback will be equal to 1 minus value. At this level, for example, for the first case, First multiply G2 times G3, then we'll see that it's a closed loop, so the output will be G2 G3 over 1 plus H1 G2 G3. Also another closed loop and a third closed loop, and the whole will be multiplied by G1 of S. And here it is also a more complex system that we have to achieve. So this was the last, the end of this presentation. What I will ask you to do is first to go through, to repeat this video, to go through each part alone, to make sure that you are well assured that of the computation of the transfer function of the Laplace transform and the inverse Laplace transform, to go through the modeling, and you have 2-3 different examples mainly for the electrical systems. So you do the electrical systems first, and you make sure that you are able to get the output of the electrical system modeling using the mesh current or the node voltage. Both can work. Then make sure that you understand really the transfer function and the 3 different types of transfer functions for a closed loop system. And I repeat, it's for the closed loop system. So the open loop, the closed loop, the feed forward are for the closed loop system. And to go through the other presentation type, which is the state space presentation, to make sure how to define a state space system and how to calculate it, and how to go from a state space presentation to a transfer function presentation, and at the end to notice the different phases of the block reduction in order to get a single block between the input and the output. So you have about 4 or 5 exercises to do and to submit them to me. In all cases, if you have any question, I'll be really happy to answer. Thank you for your attendance and your presence.